take any questions.
Thank you very much, Brenda, for this very nice talk. Is there any question? So we have still a couple of minutes. Oh, okay. David, please.
Yeah. Hi, Brenda. Nice talk. Very nice talk. I know that we discussed this before, but I'm afraid I don't remember the answer. I noticed the actual time for the computation in your slides. That was quite slow.
Very
You
slow.
have been doing work on improving that?
Yeah, it's a tricky question, David. Chemistry is inherently slow, and I would say we can almost say fundamentally, if one is moving around nuclei, there's a time scale for doing that in solution, given all the stochasticity, and that's always going to be slow. That's never going to compete with electronics. And so that's not the place where I think we win. If you want to go faster, then you can move around electrons. That's a different setup. That's basically photochemistry. And some people have pursued that, but it's difficult to control. So, molecules are not the place where you're going to see speed, but it is the place where you can see thermodynamic efficiency. You can also see implementations that are kind of autonomous, where you program, you release it into the environment, it does what it does, and it can work in different media. So it sits in a different place. Speed is just not the mountain that I'm going to climb. Maybe others would.
Okay, thank you.
Tom?
Thanks for the talk, Brenda. Very, very interesting stuff. Obviously the idea of thermodynamic efficiency with molecules, as far as I'm concerned, boils down or requires you to be only doing the computation with a small number of molecules, right? Or whatever, right? So the reason cells are efficient is in some sense is that they've got one piece of DNA that, and they're copying it once or whatever. How many molecules per bit do you have, and what's the lower limit on that, do you think?
Yeah, it's a good question. So it depends upon, for us, it absolutely depends upon the density of the information that you're storing, right? So if you're low density, we can play a lot of games where we're mapping, hundreds of bits to, let's say, one molecule. But right, that's low density. If you want high density, then we do have to go to the limit of essentially one molecule per bit if it's very high density. So we don't get around that part. Now for, the computation, the question for us is, how many molecular bits do you really need to do different computations? And sometimes it's not as many as you might think. And so your point is absolutely right. But I would say, this is a setup where if you're looking at super high density information, right, we are going to have to be using lots of molecules.
I think you're giving credit to me for the wrong thing. So what I was trying to say is, as far as I understood your molecular storage thing, you have I don't know 10,000 different molecules, and the presence or absence of that molecule is a 1 or a 0, right? In your storage.
In the worst case.
My question is, how many copies of the molecules do you need? Are you talking how many molar? Because that very much determines your efficiency, right? Everything scales with that number.
Absolutely. Fair enough. I see what you're saying. For us, it's a few copies to do most things. So we can detect down to easily a few copies. So we're talking about 5 to 10 copies is essentially all we need.
Okay. So that's
with this equipment. Now, I don't know, I want to go on a long tangent, but amplification is harder for us than, let's say, DNA. So they're different advantages and disadvantages.
Thank you.
Okay, so as a last question, Songela, please go on.
Hi, thanks for the talk. I have a clarification question, which is that how do you understand the order of the bits that are present rather than just the presence or absence of the molecules?
So as long as we know which molecule corresponds to which bit, we don't need to know the precise ordering. So, at the beginning when we store information, we know which molecule represents the bits of our information that was ordered originally. But when we store it chemically, as long as we know the chemical identities, we no longer need that information. Like we said it at the beginning, we don't need to know it in the experiment, if that makes sense.
Or I guess I'm a little confused about how the so you're saying each molecule corresponds to one bit in the array that whose order you've essentially predetermined?
Yeah, so when we have a bit string, we know that molecule A corresponds to bit 1, molecule B corresponds to bit 2, molecule C corresponds to bit 3. And so then all we need to do, so we've set that from the beginning with our text, just the kind of the mapping of our information. And then we can throw the molecules in our solution or not, and we don't need to order that throwing in or reading out because it's already.
Okay, so that's why you need the one molecule per bit thing. Okay, thank you.
Yeah, there are other compression schemes, but that's the basic idea.
Okay, thank you very much again for this very nice talk, Brenda. So our next invited speaker is Shantanu Chakrabartty. Hi, Shantanu. Yeah, okay.
Okay, let me see. Okay, which screen do you see? The presenter view or the normal view, the slide?
Yeah, I think presenter review is better for recording. If I ask to Tom or Jeremy as a host.
I think what you had earlier was fine. Yeah,
Okay.
Yeah.
it was good. Yeah.
Okay, and let's see. Okay, I'm trying to see if I have a laser pointer. Okay, can you see the laser pointer?
Yes, it works, right.
Okay, so shall I start?
Yes, please.
Okay, so thank you for inviting me. This is my first attendance to this workshop. I actually met David a year ago. We had organized this Edwin James Symposium at WashU, where we were discussing different application of statistical mechanics and his legacy, and that's where this conversation started. So I am essentially an electrical engineer. I work on a lot of IC designs. So this talk that I'm going to present is kind of going to be my foray into this domain. So I hope that by the end of this talk, I'm going to be able to present a simple non-equilibrium neuromorphic learning model. And the reason why we are trying to use this abstraction is because we want to get an estimate of energy dissipation. So the caveat here is that you will see there are lots of first order approximations. So again, and that's where I feel that this community can help in making refining this model better. And then because we have these devices fabricated, we can always give you the data for further analysis. So my motivation, I will start this with looking at this high-level picture. Okay, what is the energy cost in training a brain scale AI? And I'm going to show this plot, which a lot of other people have shown before, but I will present it in a different context. On the x-axis are the number of parameters in the model, and on the y-axis are the number of operations that are required to train this AI model. And on these dots, there are several, what I'm showing are several of the state-of-the-art AI models, ranging from GPT-3, 4. So what you can see is that as the number of parameters, training parameters are small, the number of operations that takes scales quadratically. But then what's happening lately is because of the transformers and other things, the number of operations that are required typically now scales linearly. And this is because, first of all, one may not have enough computational juice to train an entire full model, or the transformers are efficient enough that you don't need to do pairwise interaction between the parameters. But the reason why I'm showing this graph is I want to use this trend to estimate, let's say if I want to train a brain scale AI. And when I say brain scale AI, I'm going by a very simple metric, which is the number of synapses in a human brain, about 10 to the power of 15. I'm corresponding this to the number of parameters that would be there in your AI model. And then if I take the best possible extrapolation, which is this linear scaling, it gives me about 10 to the power of 27 operations. I haven't defined what exactly these operations are. Typically, it's floating point operations, but I'm just saying you need about 10 to the power of 27 operations. So what does this figure mean? So if I run these operations on, let's say, a best case FPGA, which is the state of the art, which is about 1 TOPS per watt, it will consume about 1 petajoules. But if I try to implement this operations on the best possible computational platform that is currently available, that is about 10,000, about 100 TOPS per millimeter squared. This is the computational density. It will take about close to 300,000 years to train with these many number of operations. Now, Cerebras, as many of you might already know, there are wafer scale platforms that actually can do many of these computations in parallel. But even with a wafer scale, it will still take 8 years to these many number of operations. And again, these are very rough estimates because it's possible that there may be advances in AI training algorithms that you may not need about 10 to the power 27. But essentially, this is highlighting that there is a problem. So the question is, why do we have this energy bottleneck, and what can we do with this? So typically, when you talk about training bottlenecks, there are 3 types of walls that we encounter. The most popular ones that everyone discusses is this memory wall. And that shows up because the standard computer architecture, the memory and compute are generally not co-located. So you need to bring the data from the memory into the compute unit, and that takes energy. So here in this diagram, I'm showing that the energy is a separate entity that feeds in something to the compute and the memory blocks. So for this, there already exists a paradigm that everyone believes that if you can co-locate compute and memory, you might be able to overcome this memory wall. In fact, this paradigm came from the neuromorphic community, is again because synapses do computation locally in proximity to the neurons. And that principle was adopted by many of these new AI hardware architectures. But for training, you have these other 2 performance walls that you have to worry about. First is for standard computing like inference, you might get away with 6 bits of precision or even 8 bits of precision. But for training, the number of precisions or the resolution of precision matters. And then typically the write energy to update the parameters in a memory, generally that energy is higher than actually reading the memory. That may not always be the case, as probably, I don't know, maybe in molecular memory, that might be a different trade-off, but at least in a standard semiconductor memory, that's one of the challenges. The other performance wall is a consolidation wall. And this shows up because there is a limited memory capacity that one has. So it means that when you're training an AI model, you can only keep certain parameters in a short-term memory. And then you have to keep pushing some parameters into a long-term memory and bringing it back. So in some sense, this is equivalent to what in neuromorphic community we call consolidation, which is talking about, like, okay, some parameters, for example, are important for optimization. You keep it in the main memory, and then you keep fetching it back based on the importance of that parameter. So typically, this repeated fetch from this memory hierarchy also creates an energy bottleneck. So the question that we have been asking is, okay, is there a neuromorphic solution to this, to the update wall, consolidation wall? So before we talk about what the solution could be, let me first highlight, like, okay, what happens when you train with a conventional physical memory? So typically, I'm going to assume that when you're learning or training a system, you're updating or you're minimizing some kind of a loss function, which means that you're updating the weights or the parameters. So initially, you minimize the loss function during the training phase, and then hope that after the training phase ends, you solidify the weights, you don't change the weights, and then you use it for inference. So this is kind of shown in this very simple cartoon. So if I take a standard memory model, so here I'm showing the states of the memory by this parameter W, N is here the time. Typically this memory, these two states are separated by an energy barrier. So I can think of that as I'm updating the memory, I am kind of updating the states. I'm making a state transition from this to this state. And making this state transition takes a certain amount of energy, which is proportional to the barrier. Okay? So everyone, and this is the conventional approach for updating the memory. So when you look at how much power will you dissipate when you go through this single operation, and I'm going to assume a non-reversible operations, I'm not doing anything fancy. Essentially, whatever energy I add to this state, I'm dumping it out. And that barrier height is typically determined by the precision and the retention of the memory. So the delta here is the precision that is required for the updates. So if I use this very simple formula, typically based on the barrier height that you use in conventional memory, it's about 10 to the power of 13 minus 13 joules per bit. This simply multiplying by that 10 to the power 27 will give me that 1 petajoules at a 10-bit resolution. So if I do this first order calculation, this is where I can get that number. So now the question is, okay, what can you do better? So this is a concept that we had proposed about 3-4 years ago. So we call it learning in memory. So again, we are trying to minimize the loss function. But now what we do is that we adapt the height of the barrier. So initially, when the weights have to be updated quickly, we keep the barrier low. And because the barrier is low, it means that it requires less energy to move this, make the state transition. Of course, this will introduce errors, but we hope that the learning process is going to take care of that error. So initially, we keep the retention of the weights to be low. And then with time, we make the barrier height high, so then the retention goes up. But what this also means is that I'm dissipating less energy in the initial phase of the training. So we have demonstrated this type of a memory before. So where in this case, I'm showing an experimental result. When you're programming this memory repeatedly, you can see that the updates keep decreasing over a period of time, which is equivalent to increasing the height of the memory barrier. This concept is also called metaplasticity in synaptic literature, but effectively it means that I'm modulating the height of the barrier up and down. So the question is, okay, what if I use this type of a scheme where I'm changing the barrier height repeatedly as I'm training the system? What is the expected energy dissipation of this? Okay, so, but one can think that if I use this approach, initially, because the barrier height is low, it could be that this trajectory can take many different paths to the solution. Okay, so it means that what I need, the external energy, is to correct for these paths so that they end up at the same location. And then you have to do some kind of a gradient correction. So this delta E I'm showing an external energy has to move the trajectory in the right direction. So these are the two energy dissipation mechanisms that I have to worry about for this. Okay. So this principle has a neuromorphic origins. And the reason being because the retention and synaptic plasticity are related to each other. This is commonly seen in the structure of the brain. So for example, in hippocampus, which is so-called the working memory, you have updates, you have memory units that are, vice versa. I can talk about neurons too. The memory is equivalent to, it's a low retention memory, but it allows for more frequent updates. But then you have this neocortical memory, which is long-term memory, which effectively supports a high retention, but they are less frequently updated. And these two memory systems are coupled with respect to each other. From an engineering point of view, effectively, these two memory systems work like this, where you have a register, which can be updated quickly and more energy efficiently. And then on the higher end, where you're talking about high retention memory, they work like SSD or your non-volatile memory, which has a high energy barrier. And everything works like a single flat memory system. Okay, so now the next few slides, I'm going to go a little bit into the way we are approaching to estimate the energy efficiency limit for this type of this type of an approach. Okay. So I will start with a very ideal abstraction. Our goal is to combine memory, compute, and energy together. So into one single entity, or I would say architecture. So I will start with a very simple abstraction like this: a capacitor, a resistor, and another resistor. So here the model is that the capacitor can act as a source of energy and also a memory. The resistor whose value can be changed can work as a compute element. And then these two units are connected by another resistor, which is modeling an interconnect. So what we know, again, if I use a standard circuits 101 result, if I charge the capacitor, this capacitor is going to decay according to this exponential condition. I can write this a little bit differently, talk about the current that is flowing out from the capacitor. And I have written this in a slightly different way where everything is inside the exponential. But now, what if I change the value of the resistor such that this resistance goes to infinity? Okay? So if this resistance goes to infinity, it means that at some point in time, the capacitor cannot leak the charge. So that means that the value of this weight now will converge to a different value, will not go to zero, or will not go to its equilibrium condition. This steady state weight is what we are trying to compute here. So by changing the value of the resistor in a certain way, we are trying to modulate the trajectory of this so that it converges to a specific value. Now, because we are simultaneously changing the resistor, this differential equation becomes a little bit difficult to analyze. So what we do is that we discretize this. We say that, okay, we are going to change the resistor in steps. So, but if you look at this equation, this J, which is the current, I can model everything inside this exponential as an energy barrier function that changes with respect to time. And then this quantity tells me what is the maximum rate at which, or the maximum current that is allowed. In fact, this is important because this is also modeling the interconnect. Because it's telling you that the interconnect has a certain latency and a delay, and the maximum rate that this interconnect can pass is approximately given by this Jmax, which is this quantity. From an energy barrier diagram point of view, this structure will look like this, where each transition over here is given by this current. So now when I transition to analyzing the system, I will replace this J. I can divide this by charge. This will become equivalent to probability flow. So rate of probability change between the states Wn and Wn minus 1. So this system can only move in one direction because the capacitor only leaks in one direction. So how do I make sure that I can do bidirectional change? So I can add two of these elements, and then I can simultaneously change the resistance in a positive or a negative direction. So that way I can look at the difference between the voltages across the capacitor, and that will give me the weights now. Okay. So if I start with this baseline equation, which I had before, if I perturb these two systems in a differential manner, so let's say with delta E plus and delta E minus, they are different from each other, which means that the rates that I'm looking at perturbed with respect to the baseline rate is plus half and minus half. So the equivalent rate is still Jn. Then what I can do is that I can model this system using this. This diagram is commonly used in device physics. It's an energy band diagram. What it shows is that I have two different levels of energy levels, and the forward flow of current over here is higher because the energy level over here is higher. This is the barrier height. And then the reverse flow of current is weaker or less because this level is lower than the top of the barrier. Okay. So this diagram is general enough that it can model many different things. Here, Jn0 could model the thermal fluctuations, and then Jn over here can model the net flow of current. So there are a lot of things that one can do with this baseline model. So if I manipulate these two equations, I essentially get this master equation, which is telling me, okay, how the energy barrier is related to the difference between these two energy levels. Okay, and then it also connects the net flow or of current in this case, but you can think of it as a probability flow as well. Okay, and so this is the diagram that I'm going to use for the rest of the few slides over here. Okay, so once we get to this equation, I can now place something, actually this is going to lead to the core tenet of this talk, which is this energy barrier versus energy gradient plot. Okay, so what I can do is that first, let's say I assume I normalize this Jn over Jmax to be this quantity. And if I plot this equation, I get these ensemble of curves. On the x-axis is delta E, on the y-axis is this energy barrier, and then this rate, normalized rate, changes from 1 to 0. So remember, the rate Jn cannot exceed Jmax. Okay. So this y-axis represents the height of the energy barrier or the memory retention. The x-axis tells you the energy gradient. And then there is this region, which is this inadmissible region, which effectively says that the rate cannot exceed more than 1. Okay. The important thing is that if you take a limit of this equation, let's, for example, delta E goes to infinity, you actually recover the Landauer limit. So you can get KT log 2, and then you can also recover another fundamental relationship, which says that, okay, when the energy barrier is 0, the state could be in 3 different possible states. It could be over here in the middle or on the other side. So that means that you have log of 3 because of that. So, so this equation captures many key concepts that we are familiar with in thermodynamical computing. But from a device physics point of view, the thing which I like about this equation is that if you take the limit, not the limit, but make delta E to be large, this thing becomes equivalent to this, which is saying that the current is linearly proportional to the energy flow, which effectively is what we observe when we measure current characteristics. So what can we do with this and how is it connected to learning? So again, starting from this plot, remember, what do we want to do for training? We want to make sure we change the weights, but if the training is successful, the rate has to go down to 0 asymptotically, because it has to slow down, which means that there are many different trajectories that are possible on this phase space. It starts from somewhere where the rate is large, and then slowly it has to go all the way to, the rate has to go to 0, which means that you're traversing this curve. Now, at the same time, what you want is that after you have learned the weights have to be retained. That means that the barrier height has to be large enough that you retain the weights that you have learned. So you have to end up somewhere over here on this curve. Okay. So the question now is, okay, along these different trajectories, how much is the energy that can be dissipated? So how do we connect this with learning? So ideally, we want to have some initial non-equilibrium state. If you let a bunch of capacitors discharge, it will get to this equilibrium state if you don't do anything. But what we do is that we change modulate the barrier of different parameters. So what will happen is that it will end up not getting to the equilibrium state, but somewhere in the neighborhood of the solution that you want. But by this time, the barrier height has become large enough that it will stop. It won't update anymore. Okay? And how do we guide this process is what the whole notion of learning is in this case. So mathematically, what we are trying to do here, we are trying to update the weights based on some gradient. Epsilon is the learning rate. You can look at the net loss of the loss function, which is delta n. You can connect this loss function to an actual energy for each weight. M is the number of parameters in the model. Beta is some conversion factor that I have included over here. And then I can combine all of these things by saying that, okay, the total energy that is required has to be greater than KT. C is some constant that absorbs everything, beta, M, and everything else. Then if I plug this in back to my master equation, I get this relationship. So I haven't yet still determined what is the value of C is going to be. But now I would include these additional constraints that the training has to stop within a certain number of operations. So this is another constraint, the speed constraint that I will include over here. J, remember, is the rate. Delta T is the time resolution of each update. So when you multiply this by the total number of parameters, this is going to give you the total operations. So if I go through the math now, how do I determine C? I can take a very special case, an adiabatic case, where the current, this flow, only changes by 1 over n. The learning rate also changes by 1 over n. And the reason why we picked this 1 over n is because this is directly related to consolidation, an optimal consolidation decay. So because Jn changes by 1 over n, it means that this sum tends to infinity. It means that the number of operations required is very large. But because we know that the final barrier height has to be greater than this quantity, where delta is the precision, what this lets me know is that C has to be equal to 1 over delta. Okay? So I can then plug in the value of C, and then I get a master relationship which connects many different quantities. Energy barrier, what is the speed of computation, what is the consolidation parameter, and what is the precision of the update. So all of these important parameters are contained in this one equation. So now I can use this to estimate energy dissipation. So energy dissipation here would be total number of parameters times the energy flow, or the rate of flow, times the update energy that I dissipate per update. Delta T is the time resolution, and then this is the final potential energy, or the energy that is stored in the barrier itself. I can apply these constraints that the total operations equivalent, total net operations has to be constant, and then the final energy barrier has to be equal to this, because I have to retain the weights as well. So when I use these equations, I end up with this another relationship where effectively all these other physical parameters like delta T disappears, and it only depends on the number of operations and the height of the energy barrier and the way I'm changing the flow. So there are two different variants that are possible based on this master equation. So one, what I could do is that I could apply energy gradient. And so each step, I am dissipating a delta En of energy. The beauty of this equation, of this formulation, is that I can now plug in different scheduling rates. Like if the current rate changes by a factor of this, if the consolidation changes by 1 over n, I can get a closed form solution of the total energy that is dissipated. The important thing here is that it shows two key things. First is there's the static energy dissipation, and then there's the dynamic energy dissipation. Dynamic because it depends on the number of operations that I'm using over here. Here, this is the Riemann zeta function. There could be another variant of this where I don't apply the gradient, but what I do is that I update the memory based on the standard procedure, where I bump the state, and then at each point in time, I'm dissipating an energy which is proportional to the barrier height. If I do that, the solution looks a little bit is little bit different, but the closed form solutions is difficult to get. So we have used these equations to determine the energy estimates for a typical AI workload. So here, x-axis is the total number of parameters, goes all the way up to trillions of parameters. What it shows is that, yes, here the dark red is the reported energy for some of these parameters. So these